When a transformer secondary feed supplies a panel board, a main breaker is required. An MLO, or main lug only, panel is not an acceptable substitute in this application. Overcurrent protection for the feeders is essential and must be sized according to the ampacity of the conductors and the equipment they are serving. This protection can be achieved through circuit breakers or fuses installed either in the panel board itself or in a separate distribution panel board. The primary disconnect for the transformer does not function as the overcurrent protection for the transformer or the feeder wires. Transformers generally incorporate internal overcurrent protection mechanisms such as a primary fuse or circuit breaker. However, the feeder overcurrent protection must be provided separately on the secondary side of the transformer. It is important to understand the function and purpose of overcurrent protection devices. Overcurrent protection devices are designed to protect electrical circuits and equipment from excessive current flow, which can cause overheating, damage, and even fires. These devices include circuit breakers, fuses, and other protective relays. The primary function of an overcurrent protection device is to interrupt the flow of current when it exceeds a predetermined safe level. This is typically achieved by sensing the current in the circuit and, if it exceeds the set point, tripping a mechanism that opens the circuit, stopping the flow of current. Circuit breakers are electromechanical devices that automatically interrupt the flow of current in a circuit when an overcurrent condition is detected. They can be reset manually or automatically after the fault has been cleared. Circuit breakers typically consist of a bimetallic strip or an electromagnet that responds to the heat generated by the current flowing through it. When the current exceeds the breaker's rating, the bimetallic strip bends or the electromagnet trips a latch, causing the breaker to open and interrupt the circuit. Fuses are another type of overcurrent protection device that operates by melting a fusible link when an overcurrent condition occurs. The fusible link is a conductor made of a material with a low melting point, such as zinc or tin. When the current exceeds the fuse's rating, the fusible link melts, breaking the circuit and stopping the flow of current. Fuses are typically single-use devices and must be replaced after they have blown. There are different types of circuit breakers and fuses available, each with its own characteristics and applications. Circuit breakers are typically classified by their interrupting rating, which is the maximum current that the breaker can safely interrupt. Fuses are classified by their current rating, which is the maximum current that the fuse can carry without melting. When selecting overcurrent protection devices, it is important to consider the specific requirements of the application, including the voltage, current, and interrupting rating. It is also important to consult the relevant electrical codes and standards to ensure that the devices are properly installed and maintained. Proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. By understanding the different types of overcurrent protection devices and their applications, you can help to prevent electrical hazards and protect valuable equipment. In transformer installations, the National Electrical Code, or NEC, provides specific guidelines for overcurrent protection to ensure safety and prevent damage. These guidelines address both the primary and secondary sides of the transformer. For transformers rated over 600 volts, the primary overcurrent protection is typically provided by fuses or circuit breakers. The NEC specifies that the overcurrent protection device must be rated or set at not more than 125% of the transformer's rated primary current. This requirement ensures that the transformer is protected from overloads and short circuits on the primary side. For transformers rated 600 volts or less, the primary overcurrent protection requirements are slightly different. The NEC allows the overcurrent protection device to be rated or set at not more than 250% of the transformer's rated primary current, provided that certain conditions are met. These conditions include that the transformer has over-temperature protection and that the secondary overcurrent protection is sized appropriately. On the secondary side of the transformer, overcurrent protection is also required to protect the transformer and the downstream equipment from overloads and short circuits. The NEC specifies that the secondary overcurrent protection device must be rated or set at not more than 125% of the transformer's rated secondary current. This requirement ensures that the transformer and the connected equipment are protected from overcurrent conditions on the secondary side. In addition to the overcurrent protection requirements, the NEC also specifies requirements for the location and accessibility of overcurrent protection devices. The overcurrent protection devices must be readily accessible and located in a safe place away from flammable materials. They must also be properly labeled to indicate their function and rating. It is important to note that the NEC is a minimum standard, and it may be necessary to provide additional overcurrent protection to meet the specific requirements of a particular application. For example, in applications where the transformer is subjected to frequent overloads, it may be necessary to provide additional overcurrent protection to prevent damage to the transformer. The 30 kV transformer operating at 480 volts on the primary side will have specific current requirements that need to be calculated to determine proper overcurrent protection. To determine the primary current, use the formula kV times 1000 divided by the voltage. So 30 kV times 1000 equals 30,000 volt amperes. 30,000 volt amperes divided by 480 volts equals 62.5 amps. Therefore, the primary current is 62.5 amps. The NEC allows the overcurrent protection device to be rated or set at not more than 125% of the transformer's rated primary current. 125% of 62.5 amps equals 78.125 amps. Therefore, the primary overcurrent protection device should be rated at 78.125 amps or less. You would select the next standard size breaker or fuse that is less than 78.125 amps. Standard sizes are typically 15, 20, 25, 30, 40, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, 700, 800, 1000, 1200, 1600, 2000, 2500, 3000, 4000, 5000 and 6000 amps. In this case, you would select a 70 amp breaker or fuse. To determine the secondary current, you need to know the secondary voltage. Assuming the secondary voltage is 208 volts, use the formula kilovolt amperes times 1000 divided by the voltage. So 30 kilovolt amperes times 1000 equals 30,000 volt amperes. 30,000 volt amperes divided by 208 volts equals 144.23 amps. Therefore, the secondary current is 144.23 amps. The NEC specifies that the secondary overcurrent protection device must be rated or set at not more than 125% of the transformer's rated secondary current. 125% of 144.23 amps equals 180.29 amps. Therefore, the secondary overcurrent protection device should be rated at 180.29 amps or less. You would select the next standard size breaker or fuse that is less than 180.29 amps. In this case, you would select a 175 amp breaker or fuse. Always consult the NEC and local electrical codes for the specific requirements in your area. These codes may vary depending on the application and the jurisdiction. Additionally, it is important to have a qualified electrician perform the installation to ensure that it is done safely and correctly. It is important to emphasize that the primary disconnect does not serve as the overcurrent protection for the transformer or the feeder wires on the secondary side. The primary disconnect is primarily for isolating the transformer for maintenance or in case of a fault on the primary side. The overcurrent protection for the transformer itself is often internal, such as a primary fuse or circuit breaker located within the transformer enclosure. The feeder overcurrent protection on the secondary side is separate and distinct from the primary disconnect and internal transformer protection. The feeder overcurrent protection must be provided to protect the conductors that carry power from the transformer secondary to the panel board or other distribution equipment. This protection is essential to prevent overloading and short circuits in the feeder conductors, which could lead to overheating, damage, and potential fire hazards. When selecting the appropriate overcurrent protection for the feeder conductors, it is important to consider the ampacity of the conductors, the type of load they will be serving, and the applicable electrical codes and standards. The overcurrent protection device should be sized to protect the conductors from overload while also allowing for normal inrush currents associated with motor starting or other inductive loads. In summary, the primary disconnect is for isolation, the transformer has internal overcurrent protection, and the feeder conductors require separate overcurrent protection on the secondary side. This layered approach to protection ensures the safety and reliability of the entire electrical system. The ampacity of a conductor is the maximum amount of electrical current it can carry without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its size, material, insulation type, and the surrounding environment. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity than aluminum for the same size. Different types of insulation have different temperature ratings, which affect the conductor's ampacity. Higher temperature-rated insulations allow conductors to carry more current. The surrounding environment, including the ambient temperature and the presence of other heat sources, can also affect a conductor's ampacity. Conductors installed in hot environments or near other heat sources will have a lower ampacity. The National Electrical Code, or NEC, provides tables and guidelines for determining the ampacity of conductors based on these factors. These tables are essential for selecting the appropriate conductor size for a particular application and ensuring that the conductors are properly protected from overcurrent conditions. When selecting conductors for an electrical installation, it is important to consult the NEC ampacity tables and consider all the relevant factors that can affect the conductor's ampacity. Selecting conductors with an adequate ampacity is crucial for ensuring the safety and reliability of the electrical system. The NEC provides specific guidelines for determining the ampacity of conductors, taking into account factors such as conductor size, material, insulation type, and ambient temperature. NEC Table 310.15b16, formerly Table 310.16, is commonly used to determine the ampacity of insulated conductors rated up to 600 volts. This table provides ampacity values for various conductor sizes and insulation types, based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, the ampacity of the conductor must be derated according to the correction factors provided in the NEC. Derating is the process of reducing the ampacity of a conductor to account for the effects of high ambient temperatures or other factors that can increase the conductor's temperature. The NEC also provides guidelines for adjusting the ampacity of conductors when multiple conductors are installed in the same raceway or cable. When multiple conductors are bundled together, they can generate more heat, which can reduce their ampacity. The NEC requires that the ampacity of conductors be adjusted when there are more than 3 current-carrying conductors in a raceway or cable. The adjustment factors are based on the number of conductors and the type of raceway or cable. In addition to the NEC ampacity tables and adjustment factors, it is also important to consider the specific requirements of the equipment that the conductors will be serving. Some equipment may have specific requirements for conductor size or ampacity, which must be followed to ensure proper operation and safety. When selecting conductors for an electrical installation, it is important to consult the NEC, consider all the relevant factors that can affect the conductor's ampacity, and follow the equipment manufacturer's recommendations. Selecting conductors with an adequate ampacity is crucial for ensuring the safety and reliability of the electrical system. Always consult the latest version of the NEC and any applicable local codes for the most up-to-date requirements.